pleasure. Looking at the numbers of participants, we're reaching some sort of intermediate plateau. So let's get started. It's my great pleasure to welcome Tolulope Olugboji to UTIG for our seminar. Tolu obtained a Bachelor's of Science in Computer Science from Obafemi Awolowo University in Ile-Ife in Nigeria. And he then moved to Yale, where he obtained a master's and then a PhD in geology and geophysics. He did a postdoc at the University of Maryland, the Department of Geology, and he joined the University of Rochester in 2018 as an assistant professor. Tolu has done remarkable work in seismology, and he'll be talking to us about some of the aspects there. He has received a number of awards, including Next Einstein Fellow Award from the Robert Bosch Foundation, a Firth Award from the University of Rochester, and a CIG Distinguished Lectureship in 2021. So it's a great pleasure to have Tolu here talk to us about his work on marine geophysical data and interpretations for lithosphere, asthenosphere dynamics. And his presentation today is on submarine exploration of ocean basins, silencing the singing of sediments. Tolu. Welcome.
Thank you very much, Thorsten. You did such a great, you presented such a great introduction that I think you're all aware now of what I'm going to be talking about. It is an honor to be invited. It's an honor to speak to you about the work myself and my group are conducting here at the University of Rochester. And welcome virtually to our lab here in upstate New York at the University of Rochester. We do seismology and computational geophysics here. And like Thorsten pointed out, today, when I talk about exploration of ocean basins, I just want to be very clear that we are exploring ocean basins using sensors, submarine seismic sensors, listening to earthquake-related shakings that allow us to understand the lithosphere. And the talk today will be exploring that, the solid lithosphere, and what causes transition from lithosphere to asthenosphere. The observations we'll be paying attention to are body wave observations that allow us to interrogate the seismic structure of the oceanic plates. And in particular, these observations are challenging to make. Therefore, the second half of my talk will be addressing this problem of contamination in body wave earthquake records that we are titling here the singing of sediments, and how we have been able to understand, model, and correct for these contaminations, hence the idea of silencing the singing of sediments. So again, the talk is going to be in two parts. Part one, seismology, and the view we have of ocean plates, the bottom of ocean plates from seismology. On part two, slightly technical, but I'll try to make it as engaging and as interesting as possible. But I understand that if some of the material in the second part is too technical, and that might be just because the seismology in there might be too challenging. But again, I'll make it as accessible as possible. Okay, so again, to be very clear, we are looking at plate structure. We know plate tectonics is a theory that helps us synthesize what we know about the dynamic Earth. The theory helps us understand what happens at the surface of plates, and tells us that the surface of our planet is broken into stiff plates, and most of the action, most of the interaction happens at the boundary of those stiff plates as they move past each other, bump into each other. That's where we have mountains, volcanoes, subduction zone processes, earthquakes, tsunami, and all this dynamic activity happening on the surface of our planet. What is more challenging, though, is trying to understand where at depth, plate-like behavior transitions to non-plate-like behavior. At depth, where's the transition from the solid, rigid part of the plate, part of the of our planets? That's the lithosphere, crust and upper mantle, solid, rigid lithosphere. Where's that transition from solid, rigid lithosphere to our asthenosphere? And what is the major cause of that transition? In particular, when we look at the seismic observations, trying to attribute a cause to the transition from lithosphere to asthenosphere becomes more challenging. But let me clarify that regardless of the debates about what the transition from lithosphere to asthenosphere is, to first order, we know what makes plates plates. We know what causes the rocks to be rigid and what causes transition from rigid behavior to non-rigid behavior, and that's temperature. To first order plates, the simple idea underlying plate-like behavior is temperature. And this is very well captured in this illustration here, and even in the first order observations of things like topography and how topography varies with age. Plates, new oceanic plate is formed at a spreading center. You form the crust on top of it. And as the plate cools, it subsides, it thickens, and goes on to be subducted far out in the subduction zone at around 170 million years thereabouts. And so our geodynamic models captured this behavior just using temperature. Obviously, maybe after about 70 million years, there's some difference between predictions and observation, but to first order, most of the plate-like behavior is captured by temperature. However, when we look at seismology in particular, when we look at high resolution body wave, scattered wave imaging of the plates, especially the underside of plates, the observation becomes a little bit more complicated. On the left here is a typical seismic tomographic image of the Pacific Ocean plate. And on the right here is a compilation from various seismic techniques, body wave techniques, showing where we have observed a reflector, a conversion at depth from all plates, I think mostly in the Pacific Ocean, between 0 and say 170 million years. The key takeaway from these observations, again, multiple authors, multiple techniques, is there seems to be a sharp boundary that follows a thermal contour that is still subsolidus, sharp enough to cause a conversion in different types of body wave imaging techniques. So the question is, how do we explain these high resolution scatter wave constraints? And is the thermal model that I just shared with you, showed you to first order, is that thermal model sufficient or complete to explain it? That's one of the, I guess, key questions one might ask. So that's the view of the oceans. This measurement, more recent measurements in particular, come from a technique that we call receiver functions. You will see a lot of receiver functions in the second part of this talk. So let me just quickly orient you and cue you into receiver functions. What you're looking at here is a seismic station WP1 located, I think, there in the Philippine Sea. It's the Pacific Plate there. At this station, marine seismologists collect data, earthquake data. You deconvolve from that earthquake data the source and path effects, and out pops this time series, P and S. RF for receiver function. The first pulse there, in this case colored red, is the first arriving direct body wave. And every other subsequent pulse is from a conversion underneath this station. So then the game becomes looking for signatures of conversions from within the lithosphere or across the lithosphere to a asthenosphere, and coming up with velocity models that explain these conversions. Here, for example, is then the receiver functions from station WP1. And there is the identified, the pulse from a conversion from high velocity to low velocity, this conversion here. Above, a mantellid, below, a low velocity layer, LVL, and the sharp gradient in velocity is the observation we're trying to understand. Is this indeed, in fact, the boundary, the boundary from lithosphere to asthenosphere viewed from seismology? If you just looked at the thermal structure, this is the geotherm in blue, this is the adiabat in black, and you try to explain the velocity structure based on just temperature, what you will have is in this panel here. Again, this is the isotropic velocity as a function of temperature. Notice there is no sharp velocity gradient in that blue curve. And so the way to try to reconcile the observation to what we know is to include, say, for example, something that perturbs and gives you a sharp velocity gradient. See brown curve or deep brown curve. For example, hydration or partial melt. So taken together, do these observations require that the transition from lithosphere to asthenosphere be marked by significant changes in hydration and partial melt? That's the key question. If you look into the textbooks, this is the view you might see. And this is a review work by Kawakatsu and Utada in 2017, where they've identified the picture we have of plates, the lithosphere to asthenosphere, temperature, nothing happening except at hotspots where we've got maybe a plume. And the modification based on what we are now compiling from seismic velocities, right? This again, seismic velocity as a function of depth, maybe suggests that temperature is not the only or the major control, but there is an overwhelming requirement that the transition from lithosphere to asthenosphere be accommodated by partial melts. What the structure of these partial melts is debated, but partial melts nonetheless. In this talk, I will focus on an alternative view where most of this velocity reduction, velocity gradient can be explained, we think, we and co-authors think, by a mechanism, subsolidus mechanism, called elastically accommodated grain boundary sliding mechanism. This is an attenuation mechanism. I'll go into detail about how you can get velocity reductions without needing to invoke partial melt, but just using this attenuation mechanism. This attenuation mechanism can be activated when you've got water or temperature, as one will expect for a simple view of how plates are formed. Also note that in some cases you can distinguish one model or the other by incorporating constraints from electrical conductivity, because electrical conductivity is widely sensitive to melts and water. So that's the general context of why we care and the issues surrounding this idea of plate structure and what the mechanisms are. I will argue going forward that good models must be simple, must generalize, must explain most of the normal motions, and hopefully be testable by new observations. And that's our bias, and that's the story I'll be telling today. Okay, using the compilation of mineral physics experiments, we placed these models that try to explain the seismic structure into two general buckets. Bucket one, partial melt model. This is Corrado and Park. Model two, subsolidus mechanism, in particular, elastically accommodated grain boundary sliding. Obviously, there are more models out there, and even there are some models that suggest that you can still create velocity reductions with partial melt using some attenuation mechanism. But for the focus of this talk, I will just highlight these two. In particular, because elastically accommodated grain boundary sliding, and I'll explain this in a bit, elastically accommodated grain boundary sliding has some testable predictions that we can then try to see if we can extract from new seismic experiments on the ocean floor. The prediction is that the velocity gradient should have some age dependence that follows a temperature contour given by what the experiment suggests. And then as you go to older oceans, it should flatten out because then the mechanism is governed by dehydration, by a change from water-free, water poor to slightly water, to some concentration of water inside the asthenosphere. These predictions from elastically accommodated grain boundary sliding are distinct in terms of seismic signature compared to things like partial melt, or even high resolution changes in textural properties of the rocks as you move from this portion to that portion, this idea of gradients in anisotropy or changes in anisotropic properties. Again, I highlight that in addition to these models, at least one of them making very strong, clear predictions, that you can also test them using complementary geophysical observations like electrical conductivity. For partial melt, you'd expect conductivity to increase as you move from melt poor to, melt free to melt enriched. And in elastically accommodated grain boundary sliding, the electrical conductivity will only increase when the seismic velocities are being controlled by this idea of dehydration, so water or hydrogen. So that's a key context, and everything really is framed and phrased within that context. Okay, I'll pause and ask if there are any questions, and then I'll use that opportunity just to take something to drink. Any questions at all? Okay, so let's proceed. A lot of you might be familiar or have some intuition about how seismic velocities are changed or reduced when you add melts, when you have when you have a liquid phase. The liquid phase has lower rigidity, so lower velocity. So yes, with melt in there, you should be able to reduce the velocities. You might not be aware of the mechanism, this attenuation mechanism, and how attenuation in particular can lead to reductions in velocity. So in the next couple of slides, I'll be describing attenuation in general, how attenuation leads to velocity reduction, and in particular, what elastically accommodated grain boundary sliding is. That's a mouthful, and how that also is an attenuation mechanism that leads to velocity reduction. So stay tuned. What is attenuation in general? Attenuation just means loss of energy in a vibrating system. So imagine waves propagating through rocks. And this is captured here by a general vibrating system. The black system is vibrating without any loss of energy in between its vibrating cycles. So no attenuation at all. The quality of the vibration is infinite, perfect. But for the blue system, in between subsequent cycles, you see the amplitude reduce. So the vibrating system doesn't have a high quality, high Q. It is attenuating, has a high attenuation. So attenuation is just this inverse of this measurement Q. And a Q of 100, just to give you a sense, is 1% loss of energy between one cycle of wave propagation. So if I look at a vibrating system, I calculate its amplitude in between cycle 1 and cycle 2, A1, A2, I can measure the quality of the vibration. So the quality of the vibration of the blue system there is 3.3. There is some attenuation. And yes, this system here is, it's a low quality vibrating system. What is it that is causing the loss of energy? One might think of a model like this, where the vibrating system is the elastic portion of the vibration is the string, that green string there, and the attenuating portion of the vibration is this dashpot here. So the dashpot creates friction and causes the vibrating system to lose energy. And that's the physical model I like to have in your head when we go into further detail. And this is a simple, standard linear solid. And this is how that linear solid will behave. You've got elastic portions in this physical model, perfect vibration. If it was all elastic, no loss of energy. But then if you include an attenuation, a dashpot, a frictional portion there, that will allow that system to lose energy. And in a standard linear solid, therefore, you have the attenuation described as so. And then you can have velocity reduction as you cross over from high frequency to low frequency. There's a single peak of attenuation. You can change the velocity of the system depending on how you are vibrating the system relative to the peak relaxation time of this model. In the preliminary reference Earth model describing the attenuation structure on our planet, we take this standard linear solid, we concatenate it, we just build a whole distribution of them, and we've got this model called the absorption band model. Think of it as a distribution of standard linear solids. You have a gently varying attenuation structure matched by gently varying velocity structure. So you can change velocities. The velocities, though I point out in this case, is not sharp, neither is the amount significant enough to explain what we have in seismic velocities near the surface of our planet within the lithosphere to asthenosphere, essentially. But that's the general idea. So for this particular attenuation mechanism, it is again a single peak in attenuation, and it is caused by elastically accommodated grain boundary sliding as deformation is accommodated by, deformation occurs on grain boundaries and is accommodated by elastic deformation within the grains. So here's an illustration of how that might proceed on the left. And this is again on the right, what the attenuation velocity structure is. As you move from high frequencies to low frequencies, notice there is a peak in attenuation marked by a change in velocity. And then if you transition to a lower and lower frequency, you move into that absorption band behavior and then transition to maximal body. What happens is you're deforming the grains with shear stress tau. The grain boundaries will slip, but they won't slip too far and they will be accommodated by elastic deformation. And you can move then from, again, high velocities, no attenuation, to these particular frequencies where the grain boundaries slip, and then to elastic accommodation, and then boundary diffusion and volume diffusion as you move on to higher frequencies. That's the general idea. Now, again, we point out that there are mineral physics experiments suggesting that the velocity reduction is significant enough to explain what we see at the transition from lithosphere to asthenosphere, although there's still debates about the details of these mechanisms, and there are more experiments to be done. So identifying or constraining better grain size sensitivity, the amount of shear modulus reduction, and in particular, the degree to which this mechanism is influenced by water. And this is work by mineral physicists, many mineral physicists in the community, one of whom is Corrado. But we've got now testable predictions, right? And the question is, do observations match those predictions? I showed you the age dependence prediction. Here is a prediction of what the attenuation structure should look like. Again, attenuation inverse of Q. When you take the absorption band model from Prem, but you tag onto it this grain boundary sliding model. In blue is the actual Prem Q. And in red is Q, including this high frequency attenuation mechanism. And that's prediction from our work in 2013. And it's taken a while, but it seems as if that from current new work on what attenuation structure looks like underneath a seismic array called the no-melt array. This is an array not too far away from Hawaii, deployed to measure a whole bunch of geophysical observables. But here is work showing what the Q structure looks like, the Q structure from their work, which is in purple here. And the attempt to match the Q structure, or the attenuation structure inverse of Q, using different models. And again, I point out the solid lines are the grain boundary sliding model. The dashed lines are just the simple absorption band model. Notice there's a peak in their measurements in attenuations, and that peak seems to follow the prediction. There are also other predictions, and it seems as if maybe there's a suggestion that there is a peak in attenuation as predicted by this observation, as predicted by this model. Okay, so one prediction here I've shown you more recently, and early on, following our work, following the reports where we made predictions, we looked at marine seismic experiment in this region of close to Japan, trying to test the age dependence to that velocity structure, to the presence of that velocity gradient. And this is what a marine seismology experiment might look like. They are unlike experiments on the continents because you have to, go offshore, retrofit your seismometers to be able to withstand pressures and drop the seismometers overboard and have them wait and collect data and go back and recover them. All of that technical challenges makes marine seismology unique into itself. But at the time, there was an array, and that's this array, as array from the Japanese group, and we did work trying to understand age dependence of that. I'll call it seismic low velocity zone, looking for age dependence in its depth and its sharpness as predicted by observation. Notice here that we've got then stations located on seafloor of varying age, from 0 million years all the way to 154 million years. Now, the goal will be, as we've organized the experiment, to test this model prediction of age dependence in the sharpness and depth. So I've organized the stations in such a way to highlight, to emphasize this age dependence. Transect AA cuts across seafloor of varying age all the way from 20 down to 154. And the other transects BB, CC, DD, EE, orthogonal to transect AA are oriented in such a way that there should be not much variation in their seismic signature if our prediction holds up. There are some stations that are located not on seafloor. So, when we finally summarize the results, we'll remove those stations. So again, I show receiver functions. And this is what, again, a receiver function looks like. A radial receiver function, transverse receiver function. What's the difference between the two? Up and down motion, that's vertical. Side to side in the direction of the earthquake, that's radial. And then orthogonal to the radial direction is transverse. You take your receiver functions, time as a function of back azimuth. Back azimuth just means arrival direction relative to the station of the earthquake, 0 to 360, 0 north, and then 90 east, and on and on and on. And here in this analysis, we take the receiver functions, RFR radial, RFT transverse, and we do a linear regression using harmonic functions that vary with back azimuth again, arrival direction relative to the station, to see if there are any dependencies on the arriving directions. If there's a significant component of your receiver function amplitudes that vary with back azimuth, that's an indication that you have some kind of an isotropy that's got some symmetry, preferred symmetry axis, horizontal, will give you a harmonic behavior k equals to 2, k, the harmonic order, or a layer that dips significantly, so harmonic order k equals to 1. So, people who are familiar with Fourier analysis, this is something similar akin to Fourier analysis, but this Fourier analysis or some kind of spatial Fourier analysis applied to the receiver functions. What that allows us to do is to take this measurement and collapse it in such a way then that you can simplify. You got one summary stack, and then any other stack that should vary with back azimuth if there are indeed significant variations and if they can be partitioned in such a way. For this station, station T06, most of the amplitudes do not vary back azimuth, suggesting that the conversion, the velocity reversal marked by that mantle to low velocity zone is accommodative or very well explained by just anisotropic velocity reduction. We did that for all the stations, and this is a summary of that experiment, showing again transect AA and the other transects orthogonal to it. And here in the open circles, I'm highlighting the signature of what is often called the seismic LAB, but remember this is just a velocity reversal. And just by a quick perusal, you see there that most of the variation is marked on transect AA. On the other transect, not so much variation. Compare, therefore, the prediction with the summary, and it seems as if this age dependence is borne out in this, at least this seismic exploration, this investigation of residual functions in this location on the planet in the oceans. So again, another prediction suggesting a compelling control of these signals by elastically accommodating grain boundary sliding. So that's the end of part one. So, some might suggest that this is compelling evidence. Well, there are other observations that we might try to explain. But, I glossed over this particular issue actually after publishing this work. There was a comment suggesting that residual function estimation on the seafloor is not robust. It's not robust because there is significant noise, in particular noise coming from sediments. So the next half of this talk will look at this issue of noise in submarine seismology in general, and in particular, the issue of noise coming from sediment reverberations, sinking of sediments. This idea that earthquake waves, as they move from the earthquake and arrive at the receiver, you're trying to understand the conversions from the cross-mantle interface of some mantle layering or some mantle layer, that they will get trapped in a sediment waveguide, ring, reverberate, and contaminate your record, making it difficult to do crossed-in mantle lithospheric imaging. So yeah, so that's what I will be discussing in a bit. This is uniquely a problem, obviously, of stations that are at the bottom of the ocean. In this compilation here that I showed you earlier on, not all of the symbols in that population are from submarine experiments. A lot of them, it turns out, are from seismometers actually located on continents. So this is an example of a seismometer located on the continent. It's a triangle and an earthquake happening further out from the seismometer. But then you're interrogating, you're trying to understand oceanic plate structure using these bouncing waves, these SES waves. They go all the way to the core, they bounce back up to the surface, they bounce back up to the core. And so the just this slight subtle behavior or change halfway between the earthquake and the station is what you're interpreting. And so you don't have this problem. There's a small class of observations that are from techniques like this. You've got a station actually on the seafloor, and you're trying to interrogate structure directly or at least very close to the station. One might argue that this is what you would like, right? This is a direct observation directly underneath the station. But for submarine seismology, you have to contend with everything else above and beneath the seismometer. So I told you submarine seismology is challenging. It's challenging for obvious reasons. You've got to go there. You got to retrofit your seismometer with this casing. You got to, put on it all this technology to tell it when to float, when to sink, when to rise. But there's also the challenge of a fluid layer above, the ocean water column, and the sediments beneath. So this is the seismometer. This is the measuring unit. In this case, that sensor has been, to the best of the ability of the marine seismologist, been coupled with the sediment layer. But noise coming from the water column and noise coming from the sediments do, in fact, indeed, we agree, contaminate the records. And this is one way to look at the spectrum of ground motion recorded from a seismic package. A lot of you might have seen this before, but I'll try to explain again. On the vertical axis is the amplitude of vibration. On the horizontal axis is the period, the dominant period of vibration. And this is a spectrogram from a terrestrial seismometer, or terrestrial meaning the seismometer is actually on land, in this case, in a vault there, I think in Arizona. And compared to this terrestrial spectrogram, this is actually a spectrogram from a seismometer on the bottom of the ocean, BB-OBS, BB broadband, OBS, ocean bottom seismometer, and also another seismometer on an ocean island, actually KIP, Kipapa in Hawaii. Spectrogram UD, up-down motion, and H1, H2, horizontals. Two horizontal directions orthogonal to one another. In this case, we know the direction of the horizontals, north, south, east, west. And so we can then draw out or do analysis that gives you the amount of energy recorded by each sensor for a particular dominant period or at a particular frequency. So period increases in this way, frequency decreases in the opposite way. The key here, therefore, is there is some background low noise behavior to the vibration on our planet, on our Earth. So this is kind of the lower floor of this spectrogram. You see there the hum, the primary microseism, and the secondary microseism. That is always there. And then earthquake surface waves are in the long period, and then earthquake body waves are in the short period spectrum. And the shortest period spectrum, you've got the cultural noise, all the noise caused by humans doing what humans do. On land, especially in a sensor that's properly well built, the amplitudes kind of hug that low noise floor. But in the oceans, both on ocean islands, that's this thicker curve, and on the bottom of the seafloor, submarine seismometer, you see the horizontals in particular hugging the higher end of that noise spectrum. So there's more noise, definitely, on seismometers on ocean islands, as well, especially on ocean bottom stations. And that's what I'll be discussing today. We know very well what causes the noise in the surface wave band for broadband ocean bottom seismometer. Typically, that is tilt and compliance. Tilt is just the idea that the seismometer is not correctly oriented with the horizontal. And so any wave on the horizontal will leak onto the, any wave on the vertical will leak onto the horizontal. Think of this being waves in the ocean, in the water column. So that's tilt noise. So that's here where information on the vertical essentially is leaking into the horizontal. That's the tilt noise there. For compliance noise, it's just the coupling of the pressure waves coming from, again, this, wave, infragravity wave, coupling with the solid Earth. So you got this wave, low frequency wave coming in at some wavelength, couples with the solid Earth beneath, causing increase in amplitude, and that's the compliance noise. They're very well understood, been studied for a while, and there's recent work that suggests that they can be modeled and corrected. So here again is an example of a vertical seismogram in this gray shaded color with tilt and compliance noise still present. And in the darker color is the tilt and compliance noise removed. For a submarine seismometer at 154 meters and a submarine seismometer at 3 kilometers. This is the methodology of removing it, and this is the references following explaining that technique. I wouldn't emphasize the math of that technique, but to show you that we know now slightly better how to remove these noise sources. Okay, now let's move to this body wave noise, which is the noise that was implicated in our interpretation of residual functions, suggesting that the interpretation is not robust. And that's this noise. So this is again in the body wave band, and this is what it looks like. So if you just look at that band, I've highlighted that with gray shaded blue colors, you see these jagged edges, almost like essentially what they are, essentially almost like peaks in the spectra at predictable intervals. And they show up here. They're not very well studied. They were implicated, people know about it, but there's not that much work on understanding, correcting, and removing them. We think we know now how to do that. There's some work in continents, but I think our work is probably the first trying to constrain it, understand it, and remove it from residual functions in the deep oceans. And what they are, again, essentially is you got an earthquake wave coming in and getting trapped in a waveguide. This is an illustration from this book here, 2013, and this has been studied in marine seismology since the 1950s, actually, studied in particular for the reverberations in the water column, and now we've extended it to reverberations in the sediment layer. The waves come in, and then they reflect at the surface and at the bottom of the water layer, essentially guided in, multiple copies, delayed by the travel time of that wave, two-way travel time of that wave in the water layer, and multiply reflected, governed by this reflection coefficients of the water and the solid earth. So trapped waves, constructive interference of such waves will lead to this behavior in the spectra, and they can get so loud that they overwhelm any conversions from deeper within. Obviously, based on this simple model, you would imagine that this would be given or influenced by the reflection coefficient and the delay time, as indeed it is. This is walked in this particular slide, which is what I'm calling the singing of sediments, one slide more or less. This is worked out for the ocean layer, but it turns out that the physics to a first order is similar for a sediment waveguide. Any questions so far? Okay, so you've got an incoming wave. Buried in that incoming wave is the earth response that you're trying to interpret, that you're trying to understand, in particular the earth response of the layer within and across the lithosphere. But that earth response goes through this filter, this linear filter, and before it is measured on your marine seismic recorder. And your goal is to deconvolve this filter, which is what we call the singing or the reverberation effect, in order to improve the images you're obtaining from your submarine recorder. Indeed, it is a filter, and this is the kind of analysis that goes and demonstrates that this indeed is a filter, a linear filter in the frequency domain. And so this is work, most of the analysis in demonstrating this behavior and correcting for it. This is work done by my PhD student, so he gets much of the credit for the actual analysis. And this is how we proceed in showing the similarity of this effect for both a water reverberation and indeed a sediment reverberation. So you get an earthquake, it converts within the moho and within the lithosphere. But before it arrives at your station here, shown by the triangle, it goes through the sediment waveguide, is reverberated. It goes through the water waveguide, is reverberated before arriving at the receiver. But the effect is very predictable, we think. And that's the effect of the reverberations in both waveguides. They are similar in form, differing only by the thickness of the layer and the amplitude of the reverberation governed by the reflection coefficient. And the filter to reverse it, the de-reverberation filter to reverse this effect, is just an appropriately matched notch filter. This is what we're showing here in the black. Notch filter matched to the reverberation effect. So essentially where you have the maximums in the reverberations, you tune by identifying the structure, tune to match minimums in your notch filter, and that knocks out that reverberation effect. So it's a selective filter. Here are the experiments showing how we proceed to model it for controlled structure, and demonstrating that indeed we can improve the inference on the MOHO and the seismic LAB after correcting for this filter. So this is what, say, a typical model might look like for a submarine environment in the deep oceans. You got a water column, sediment layer, and then you got the cross-mantle boundary, the MOHO. And this high velocity mantle, low velocity layer, identified here as LAB. You got waves coming in, converting at each interface, highlighted and labeled there. You've got positive and negative phases. And the goal in trying to understand either the MOHO or the LAB is trying to interpret the arrival times and the travel time move out of each and every of these phases. It turns out that in the case of significant reverberation, these phases are washed out by their reverberated copies either within the sediment layer or within the water column layer. And here is an example of this happening in this particular model, showing those reverberations over and above the actual conversions you're trying to interpret. The conversions that we're trying to interpret here, PMS, BPMS, PSMS, PLS, and the reverberations here are these doublets, these negatives and positives that go on and on, those delayed copies. Here you can see them because we've pushed this synthetic receiver functions to very high frequencies. But in actual receiver functions that might be obtained in a real experiment, they are at lower frequencies and they wash out the entire receiver function, making it difficult to interpret. This is the case where now we've applied that de-reverberation filter to remove and correct that effect. Notice again, this filter is prescribed by the reflection coefficient R0 and the two-way travel time, two-way delay time, delta T. To some degree, if you know what those are, you can remove that reverberation effect. So in addition to actual controlled experiments, actual synthetic experiments, we apply this same procedure, same analysis to actual data. So this is the no melt experiment that I've alluded to already. Each triangle there is a seismometer at that location, about 70 million year ocean plate. That's Hawaii for reference. That's an array of about 16 seismometer. And this is what a seismogram for one of those stations actually looks like. Red, up, down, and then blue and black, the horizontal motion. This is a very, very large earthquake. I think it's a magnitude 7 earthquake. But see the quality of the signal to noise, very low. It's very hard to identify the phases, but also even just on the horizontals, you see this already, this constructive interference behavior, this beating phenomena of waves trapped inside that sediment layer. When you look at the spectra, you see more clearly what the signature of those reverberations are. Spectra, the amplitude as a function of frequency of the 3-channel recordings, vertical Z, horizontals R and T. The grayscales there for the lines are just noise, the spectra of the noise. Notice the spectra of the actual waves, earthquake waves, has this rich sediment reverberation effects, these peaks at predicted intervals, and they become very clear when you look at the coherence, spectral coherence of the vertical with the radial, showing a prominent signature of the reverberations. The formal form of the harmonic frequencies of the reverberations have been worked out, and they have that form there, and that's what's shown by these blue dashed lines. So prescribing the velocity, shear velocity of that waveguide, and the thickness of that waveguide helps you zone in on the harmonic frequencies of the trapped waves as they constructively interfere in that layer. So showing here that yes, indeed, you do have the resonance. So these are stations with strong resonance in red, stations without strong resonance in black. Even for an array, there's some complexity, and that's future work, trying to understand when you set up that resonance or when you don't. If you take the seismogram, the fundamental resonance in this case should happen at around, I guess, slightly between maybe 0.3, 0.4 hertz. And you band pass the seismogram between 0.1, 0.5 before that fundamental resonance, fundamental frequency of the resonance. You notice a significant improvement in the signal to noise ratio for this particular earthquake. So indeed, this earthquake is being washed out by just that large amplitude resonance at this particular station, and in fact, across the array in this location. Now, if you had just done a simple band pass, you would have washed out the reverberation, conductor receiver function, done interpretation, but your interpretation will be at the low period, low frequency end. And so that's a non-selective filter. We argue that the better thing to do is to use the selective filter to knock out the reverberation frequencies without compromising the resolution. And this is a slide demonstrating how that was done, showing without the filter, after the filter, and improvements in the coherence of the phases that you are indeed trying to interpret PMS, PPMS, PSMS, PLS. Application of the filter helps you constrain better the depth to a low velocity reversal. And so this is an experiment, again, demonstrating that you can do this, and it does indeed improve the quality of your receiver function. So taking together, I've shown you a bunch of compelling, I'd hope, arguments suggesting that at least for most of the oceans, the low velocity zone observed in seismology can be explained, not necessarily using partial melts, which is highly unlikely at no melt, just from conductivity estimates, but by this elastically accommodated grain boundary sliding. And I've also shown you that the interpretation from body waves, especially using the receiver function techniques, is now more robust because we can now understand, correct, and remove contamination coming from the sediment layer that rings, makes receiver function imaging difficult. Obviously, there's more work to be done to understand the behavior of the sediment wave guide, and to apply it in more challenging, for more challenging community experiments, community deployments, an example being the ACE experiment, the Alaska Amphibious Community Seismic Experiment. And this is ongoing work in our group. Here, you have a seismic array now that traverses, moves from deep oceans across the trench into the continents. And so you've got variations in water thickness and also variations in sediment structure. And so your ability to figure out what the resonances are and correct for them is more challenging. We are working on this. But one might argue, and this might be my last slide. Yeah, this is my last slide. One might argue that understanding this behavior is significantly important for the future of exploration, seismic exploration on our planet. We've seen community experiments like EarthScope covering the entire US, continental US. And there are new experiments coming online here, experiments on the bottom of the seafloor. And these are short-term deployments, particularly this specific array experiments here. Japanese, United States, 2-year deployments. Understanding this behavior, correcting for this behavior will make imaging of both the lithosphere and even the deeper mantle possible and more robust. And there are now new proposals to have long-term deployments, a type of EarthScope in the wide oceans. Understanding this also help us build better images of the planet's interior. 70% of our planet is ocean. Understanding and doing seismology at the bottom of the oceans will be crucial going on into the future. Thank you very much for paying attention. I'll take questions now.
Thanks a lot for a great presentation. Very much appreciated. We have time for questions, and so I'll try to monitor here if you can raise your virtual hand, but if I miss you, just please speak up. Doug, please go ahead.
I'm unmuted. So thank you for your interesting talk. So I have questions about this transitional boundary. Do you often see specular reflections from that?
Can you explain what specular reflections are? I don't think
just a body wave reflection, you know. Yeah, a coherent body wave reflection, like you see from off the ocean bottom.
Do we always see that where now in our data?
And yes, in your body wave data, do you see reflections, clear reflections off that boundary between the asthenosphere and lithosphere?
Do we always see that? Most of the time, yes. That's a yes.
Okay.
That's a yes. From different techniques, you know, SCS waves, SS reflections. I've identified receiver functions. But yes, well, in those cases, you know, those are conversions in some cases. But yes, you would see reflections if the waves are strong enough to cause this reflection.
Because it's this transitional boundaries, we see this in permafrost, coming in and out of permafrost, where the permafrost is very resistive, melts or not. The melted zones, you know, you go in and out of melt zones. It's very big velocity contrast, and it acts like a low pass filter sending a body wave through. Do you see that same phenomena in your?
I don't know the details of what you're explaining, but if I looked at it, maybe I'd be able to say.
Well, let's say you put a wave in there from like maybe 5 to 60 hertz. What comes back is like below 40.
I got you. So it adds, yeah, I see what you mean now. I see.
Do you see any of that in this transitional boundary?
Yes, you know, I want to argue that that's exactly what you're seeing, at least when they're doing the attenuation imaging, right? So let's see if I can go up here. Now that's yeah,
you should see strong attenuation, and a lot of that.
Yes. So that's what they're seeing here.
Yeah. A lot of that can be due to not inherent, you know, heat transfer. That could be due to scattering attenuation.
Very true. Yes.
You think would that be correct?
That would be correct in general, but not in this case, right? Because they've addressed this idea of scattering related attenuation because you're looking at an array. So they've corrected so that, you know, you got an array that's got some aperture to it. And so you've corrected this idea of scattering. You're just looking at attenuation between the array, between the stations in the array as the surface wave moves from one station to the other. That's my understanding of this measurement. I'm not the one that conducted this measurement. This is the Brown group, Colin Dalton and others. If you wanted to understand more about this measurement, I'd encourage you to invite her to talk more about these attenuation measurements. But I don't think in this particular case, this is scattering related. No, I don't.
So you think it's intrinsic, like heat
intrinsic. In this case, intrinsic, and they use our model, this idea of absorption band. So this idea that it's, in our case, energy loss as the grains essentially slide past each other, causing friction. But some have argued, and for full disclosure, I should put this out there, that you can cause intrinsic attenuation with just a slight amount of partial melt on the grain boundaries. Or even just bringing the rocks near melting, but not complete into melting, will also weaken those grain boundaries. So it's an intrinsic, to answer your question, it's an intrinsic attenuation mechanism, not related to scattering, at least the way I read and interpret their paper.
Okay.
Thank you
very much.
I don't see any other hands up right now. So I guess I wonder, when you look at the different models that have been suggested for the MLD in oceanic plates, what's your view of the current scorecard in terms of different mechanisms explaining a wider range of data? So you've explained to us that there's a lot of good evidence for this grain-based mechanism. But
Yeah.
if you know, look, say it's partial melt controlled by permeability barrier, which maybe
Yes.
feels pressure, right? So you wouldn't see much of an age dependence. And then the grain boundary sliding, as you mentioned, there's different predictions. So if you just now take a step back and you look at the age dependence and all that stuff, which mechanism seems to be most reflected in the data?
I made you compelling evidence just looking at body waves, right? What I should do is take a step back, look at body waves, look at surface waves, look at some geodynamic scenarios, and ask, what's the scorecard? It's hard to argue for age dependence, like you just explained, for the partial melt model. Just looking at the body waves is just really, really hard. But someone can come up, you might include can come up with a model that allows you to localize melt that will follow some, like you said, some permeability barrier that is governed by the thermal structure. I don't know if those exist. If they do, I'm willing to open my mind to that possibility.
Yeah.
So I'd say so. Scorecard very low. About things like anisotropy, that's possible. In fact, the surface wave work from the Lamont group, Jim Garrity and others, compelling work that suggests that there is a peak in anisotropy as you move into or you move across that signature that we're seeing from body waves. So I won't rule that out at all yet. So that's still, so there is, and that does not work from Jim, but from global studies of anisotropy, pick your favorite seismologist. So that is still up there. The question is, how do you juxtapose both ideas, right? This idea of this high resolution body wave view with the, in some senses, lower resolution view from anisotropy, because most of the work uses surface waves. Somebody, a couple of seismologists come together and review that and see what how they put those two together. But as it's really challenging, as I just suggested, we really do need seismic arrays that stay around for at least 3 to 4 years, and a couple of them, so that we can then begin to, like you say, maybe rank these different mechanisms. That's my thought. Yeah.
Thanks. And so I still don't see other question. Then maybe let me ask another one. So I remember I was at a dinner at John Herland's house in Tokyo, talking with Kate Reichert about that. And she got really kind of upset to me when I told her that I really don't care about the MLD, as long as the mechanical boundary layer still follows half space cooling. And so my concern at the time was like, okay, so this is partial melt, but if it's all baked in, then the existence of the MLD is a very important constraint on how a plate is made. However, if the viscosity, for example, doesn't care about it, then mechanically temperature is still the governing thing. So what is the mechanical implication of the grain boundary mechanism?
Thorsten, Becker, I'm with you 100%.
Which part?
On the half space cooling part. I feel like we shouldn't throw away models that have done a great job at explaining a lot about our planet very, very quickly. Or when we do modify it, we should modify it systematically. So I'm with you on the half space cooling model part. So back to the issue of why should we care? Yes, we should care if it does significantly influence the viscosity of the rheology at the time scales that plate tectonics cares about, so long time scales. And this is the point here. The point here for this model is that whatever signature you're looking at in seismology in the seismic record is at the seismic deformation timescales. Is at the timescales at which the waves sense microscopic structure of the rocks. So how long does it take to go from rarefaction to compression for a compressional wave? How long does it take to go from one cycle of the shear wave to the other? That's the time scale at which seismology is looking at this, right? And let's try to explain that using different techniques. Yes, if there is melt, if melt can explain that significantly, at all locations, MLD, ocean, then yes, that's a significant process. But if temperature, like we suggest here with this mechanism, can explain it, then you don't need to refine hotspot cooling model on 70% of the surface of the planet. Right.
But let me ask you specifically, are there constraints on the effect on viscosity of this grain boundary mechanism? My guess would be that it should actually perhaps matter more for viscosity than the partial melting, because if it affects attenuation in that sense, then usually the guess is that viscosity will also be affected because they're linked on the sort of microphysical mechanism. So what I'm trying to say is I could see that this mechanism might actually be more relevant mechanically than others.
I hear you. My naive interpretation is not necessarily.
Okay.
Because look at if you look at the plots I showed you, this is a distinct mechanism that is just happening at grain scale. Only when you deform at the relaxation time of the grain boundaries, not at all. It is agnostic to long period deformation, absorption behavior. That's what my naive understanding is. But again, if you want to have a solid discussion about this, you know who to call. The Fowle Jacksons, the Corrados, and all the other mineral physicists who tell us what rocks do when you squeeze and when you squeeze.
I'll pick up my red telephone right now.
Exactly. But that's my understanding of this.
Thank you, Tolu. Do we have other questions? If not, then let's thank Tolu again. I put the link to the next meetings in the chat. It's also the Google Doc. And if you're not signed up to meet with Tolu, he kindly agreed to join us for a social hour at 5 p.m. So please make sure to see you then. And let's thank Tolu again. Thanks a lot.
Thanks.
Thank you.
Guys.
Very interesting.
Thank you, Doug. Thank you, Thorsten. And thank you, Constantine.
Thank you. I'll see you in the next meeting shortly.
Sounds good.